Hello and welcome back to Set Theory. In the last part, we gave a big picture overview of the 10 axioms of set theory. If it was a lot, don't worry, you weren't supposed to understand all that. That was a brief overview of where we're headed. Today, we really begin, and we're going to take a deep dive into the first two axioms of set theory and see what we can prove from them. The axiom of the empty set basically says that there exists a set which has no elements. There exists a set A such that for all sets B, B is not a member of A. In other words, there exists a set with no elements. Axiom 2, the axiom of extensionality, says that for any sets A and B, A is equal to B if and only if for every X, X is in A if and only if it's in B. This part of the formula says that anything that's a member of A also has to be a member of B, and anything that's a member of B has to be a member of A. In other words, A and B have the exact same members. So the whole thing means A equals B if and only if A and B have the exact same members. In other words, two sets are equal if and only if they have the exact same elements. Now, there's something very important I want to address here, is that not all books have these two axioms as I've written them here. For example, some books don't have an axiom of the empty set. Likewise, some books give a slightly different version of the axiom of extensionality, and this double arrow becomes a single arrow. At the end of the video, I'll explain more about the variations and the reasoning behind them. However, in set theory, what's most important is not the axioms themselves, but what we can prove from them. Although it may be confusing that different books give slightly different axioms, we need not be alarmed as long as what we can prove from the axioms remains the same. In other words, the different ways end up being logically equivalent. But for the purposes of our course, these are the first two axioms. Let's see what we can prove from them, shall we? Theorem 1, uniqueness of the empty set. There exists a unique set with no elements. Okay, so recall that axiom 1 told us there exists a set with no elements. However, it didn't tell us that there can only be one set with that special property. This theorem says that there exists a unique set with no elements. Let's write that in quantifiers. There exists a unique set A such that for all B, B is not an element of A. The backwards E with the exclamation mark means there exists a unique. What does unique mean? It essentially means that any other set having this property must be equal to A. We can rewrite that with normal quantifiers. This part says A is empty. This part says that if another set A prime is empty, then A prime has to equal A. This part means and. As you can see, having to write everything in quantifiers can get overwhelming pretty fast. Although in principle it's possible to do set theories super formally, writing everything in quantifiers, we're humans, not computers. Therefore, for the most part in this course, I'm going to only use quantifiers when it makes things more readable, and I'm rarely going to write something like this. How do we go about proving that there exists a unique set? First, we have to prove that a set exists, and then we have to prove that if another set A prime is also empty, then A prime has to equal A. So let's prove it. By axiom 1, that is the empty set axiom, we already know there exists some set with no elements. Let's just call it A. So that shows existence. But how do we show uniqueness? Well, here's what we do. Assume A prime is also a set with no elements. Whether or not it's equal to A or it's distinct from A, we're not making any assumptions about that. We want to show that A prime equals A. This will show that A is the only set with the special property. How do we show two sets are equal? Well, the axiom of extensionality tells us that two sets are equal if they have the same elements. That is, we got to show that every element of A is also an element of A prime, and vice versa. Every element of A prime is also an element of A. But guess what? This is true. Why? Because A and A prime have no elements. If you want to think of it in terms of quantifier logic, X is an element of A. No matter what X is, this is going to be false because nothing can ever be an element of A. And since A prime's empty, this is always going to be false. So the whole statement says false is equivalent to false, which is true. So we proved the theorem. Now this is important. Whenever we prove that there exists a unique set having a certain property, we're allowed to invent a new symbol for it. So we're going to define this guy to be the unique set which has no elements. Now, in principle, one could do set theory without ever having to invent new symbols. One could get around having to use this symbol by using quantifiers every time. However, as you could imagine, that would get ugly very fast. Speaking of making up new symbols, let's talk about subsets. We write this, meaning A is a subset of B, when we really mean this. Every element of A is also an element of B. In other words, saying A is a subset of B is the same as saying every member of A is also a member of B. You can think of this symbol as shorthand for this ugly expression. In principle, we could keep using this ugly expression every time, but that would be such a pain. Here are some basic properties of subsets. Let's prove them. The first three properties have special names, which I put on screen because it might be helpful for some of you, but you don't have to know the names for now. Let's prove one first. We want to show that A is a subset of A. How do we do it? Well, if we remember our definition of subset, it's this, right? So this just means for any X is an A implies X is an A. And this is true. Why? Because these are the same, so the implication's always true. Next, let's prove 2. Notice it's an implication. So what we want to do is we want to assume that the left side is true and then try to prove that the right side is true. So we assume that both of these are true, and we want to show that A equals B. How do we do it? Well, let's rewrite this in English. This part says every element of A is also an element of B. This part says every element of B is also an element of A. By the axiom of extensionality, these two things tell us that A has to equal B. So that proves 2. Now let's prove 3. We want to show that if A is a subset of B and B is a subset of C, then A is a subset of C. So let's assume the hypothesis. Assume A is a subset of B and B is a subset of C. We want to show A is a subset of C. What does subset mean? It means that anything in A has to be in C. In other words, we want to show that for any X in A, X also has to be in C. We can also write this in more compact notation. The strategy for proving a quantifier statement like this is you assume you have some random arbitrary X that's an A, and you got to prove that it satisfies whatever properties in here. And even if no such X exists, for example, if A is the empty set, there's no X in the empty set. Nevertheless, in that case, it's vacuously true that for all X satisfying that impossible condition, that this holds. So let X be an element of A. We want to show that X is an element of C. How can we do it? Well, since A is a subset of B, that means any element of A also has to be in B. Therefore, we know X has to be an element of B. Likewise, since B is a subset of C, X has to be an element of C. And that's what we were trying to prove. Finally, let's prove 4. We want to show that the empty set is the subset of any set A. In other words, we want to show that every element of the empty set is also an element of A. And this is true. Whenever you make a claim about every element of the empty set, you're going to get a true proposition because there's no element that would make it false. So we did it. We proved all four of these properties. There is something very interesting about our proofs, however. To prove two, we had to use the axiom of extensionality. Proof four, we had to use uniqueness of the empty set to even be allowed to write the symbol, which in turn relied on both of our axioms. But to prove one and three, we actually didn't need to use any set theory axioms at all. Why is that? Well, let's revisit the proof of this guy here to show why. Recall saying A is an element of A is just shorthand for saying this. Even without any axioms of set theory, there's no way this could be false. Either these guys are both true or both false, but there's no logical way they could be different. Therefore, this whole inside is true, regardless of what X is. So we actually didn't need any axioms of set theory to prove this. However, we are using the axioms of logic behind the scenes, such as P implies P or X equals X, and other logical axioms that we probably don't even think about. However, the logical axioms are not listed with the ZFC axioms because logic is seen as separate. Set theory is the game, logic's the board we're playing the game on. Speaking of axioms, let's talk more about these. Some books state a slightly different axiom of extensionality. The only difference is that their version has a one-way arrow. It has if instead of if and only if. However, the converse direction follows immediately from logic because if A is equal to B, then there's a logical axiom or rule of inference. I'm not sure actually which you're supposed to call it, which says that we can substitute A for B or B for A. If we substitute, it turns into this, which is true. So both ways of stating the axiom of extensionality are equivalent. I prefer my version, however, because I think it's more intuitive and easy to understand for beginners. There are four different ways you can handle what I call the axiom of the empty set. Way number one is to present the axiom of the empty set as saying there exists a set with no elements without specifying whether or not it's unique. Way number two, and the way I believe some books do it, is to present the axiom as saying there exists a unique set which has no elements. Version number two is not equivalent to version one because unique is stronger than just merely existing. However, as we proved earlier with the axiom of extensionality, you can prove that if there is a set that has no elements, then it has to be unique by extensionality. Therefore, even the two axioms by themselves are not equivalent. In the greater scheme of the axioms as a whole, the axiom system itself doesn't change what you can prove and can't prove. Version number three, which is pretty common, is to not give an axiom of the empty set at all, but merely an axiom that says there exists a set, some set, without specifying whether or not it's empty. In other words, there exists an A. The reason we have this inside part is because in the syntax of logic, you're not allowed to just have nothing. In logic, you're not allowed to just write this without something after it. The reason A equals A is typically chosen is because it's always true. Way number four is to give no axiom at all. And there's a couple reasons why books do this. One reason is that some logicians consider this, that there exists some object in our universe, to be not an axiom of set theory, but an axiom of logic. Although not all logicians would agree with this. Some systems of first order logic allow you to have an empty universe and a universe where there doesn't exist any object in it, and some don't. So it depends on what frameworks you're using. Another reason for not giving an axiom at all is that this axiom is redundant, since the axiom of infinity, that is axiom number 7, tells us there exists an inductive set. And even if you don't know what an inductive set is yet, hey, at least it's a set, so there exists some set. It should also be noted that my version of the axiom of the empty set is sometimes called the axiom of existence instead, not to be confused with this axiom of existence. So question, if we replace the first axiom and just assume that there exists a set without knowing anything else about it, can we prove that there must be a set with no elements? The answer is yes, we can, but we got to use the axiom schema of separation to do it. Stay tuned, as in the next lecture, we're going to take a deep dive into this recipe for an infinite number of axioms.